Hello, let me introduce myself. I'm Rachid Alami. I am a research scientist at CNRS, and I'm also holding the chair on cognitive and interactive robotics at the NET Institute. The topic of the chair is the scientific challenge of devising the cognitive and interactive abilities which will allow a robot to perform collaborative tasks with a human partner in a pertinent, transparent, legible, and acceptable way. The applications that are targeted are, from one side, the service and assistant robot, which will assist dependent persons, and also the teammate robots, which will work or co-work in the factory or the field with humans. And my point here is that the interactive challenge of AI is fully realized in human-robot collaboration, particularly when human and robot have to decide and act together, have to share their decision, to share space and the task. And this is what we'll see in this talk. When we speak about future robot or imagine future robot, there are a large class of applications, I would say almost a majority of situations and applications where the human is present or even interacting, present in the environment or interacting with the robot or is served by the robot. And this is our topic. Of course, in the industrial and field robotics, clearly there is a challenge of the human and the robot working together side by side and achieving their work, while the robot is, of course, not equivalent to the human, but is helping the human in performing his task. Now, we know that today impressive results have been obtained in AI and robotics, but still, if we look at the distribution of domains over which the robotics can be applied, we can see that we are still here, I would say, in the narrow task, one task, known in advance situation, yet far from situations where there is uncertainty in the task which is not, or at least in the environment which is not known in advance, and also in the other direction where we enrich the robot with the ability to perform in various environments and also to achieve a diversity of tasks, broad competence known in advance, and then I would say the most challenging situation that we will face is the broad competence in environment which is not known in advance or not known in detail in advance. And today, when we see marvelous or impressive results, we are still here in this monotask engineered in advance, or even if when learning is performed successfully, we are still here in the situation where we have one task in a specific domain, which is known in advance and with little uncertainty in the future and in the dynamics of the environment. And so the difficulty that it is in front of us is still this issue of robot autonomy, when the robot is faced to a variety of environments, to a diversity of tasks, and to also uncertainty before deployment, and also uncertainty that happens in open, non-protected, non-structured environments, and particularly when they are populated by other agents. The difficulty comes also from the fact that if we want the robot to close the loop at decision level without the intervention of the human, particularly for long horizons, with respect to the knowledge available at the initial deployment states, we are still far from it today. And this is the big challenge. Of course, when we add the human there, the human-centered considerations makes the problem even more challenging and complex, but also interesting, of course. So specifically, this aspect of operating in human environments makes us imagine the robot of the future, which will not be only a tool which does things for us, but a partner which does things with us. And so it is important, it is necessary to endow the robot with social abilities in order to understand and to understand the human, and to be deployed in a way that satisfies the human and fulfills the objectives for which the robot is built. So when we add a parameter to the system, the human, when we add the human in the environment, the robot has to, the implementer of the robot, the designer of the robot, has absolutely to endow the robot with the ability to take explicitly into account the presence of the human. And by doing this, we have to revisit the robot decisional abilities. And this means that we need a robot that is far more intelligent than the robot that we have today, AI, again, perhaps also far more subtle. I don't know how if this is part of AI, but I assume it is. Now, when we speak about human and robot interactions, I will not speak about what I will call the sensory motor level. We have today this kind of robots that are able to perform in the vicinity of human with low injury risk, and which are able to adapt to the human, but not really considering the human per se. It is essentially adapting and ensuring a low risk for the human. So these robots are now existing for working with the human, I would say, or at least start to exist. But where we are today is, I would say, the need to develop an integrative approach for robot that will have to act with human. And this ability is based on study of human-robot interaction, is also inspired by work on joint activity and teamwork between humans. And we have the ambition to progressively elaborate a coherent framework for joint human-robot activity. And source of inspiration comes from a number of domains in AI and outside of AI concerning multi-agent, belief, desire, intention systems, dialogue systems, developmental psychology, and also even philosophers and psychologists who work on joint action or who constitute the joint action community. This was so important that we have started a series of workshops, and we are conducting the series of workshops on human-robot joint actions, where we bring together psychologists, philosophers, and also roboticists on this common topic of joint action, particularly centered on human-robot joint actions compared to human-human joint actions. We have already organized 11 workshops, and I'm putting here a link to where you can find information and even talks and slides of these different workshops that have been organized. I was still organizing and planning to organize future events around this topic. So this concept of mechanisms and mechanisms of joint action is key in the construction of robot. Why? Essentially because joint action, when we look at it from the psychologist, I would say, point of view, is regarded as a social interactions where two or more individuals coordinate their actions and use their social skills, coordinate their actions in space and time to bring about a change in the environment. And what is very interesting here is that we are able, we human, to not only perform actions, but also pay attention and do what is necessary to avoid situations where things go awry. And this is the basic problem of our robots, how to avoid to go awry. This is why we need to equip the robot with decisional capabilities to perform human-robot joint action in different situations, like we see here, from a service robot to a co-worker robot to an assistant robot at home or in an institution. And what is important here is to understand how we humans are able to collaborate successfully and what is necessary to be a good partner when doing joint action with a human, and what a human will expect from a performant robot that will perform joint action with her or him. And so this takes us to this problem of endowing the robot with decisional processes that will allow it to face this problem. So our approach is a task-oriented approach, essentially, and it can be represented like we see here in the figure. We have a human, we have a robot, there is something to do, and the human and the robot are can perform multimodal dialogue to help perform the task. And also, and this is very important, they are in a situation where they mutually observe the activity of the other. So the robot observes the human observes the robot, and what is very important is to endow the robot with the ability to reason about the fact that it is observed. This is what is represented at the right side of the slide, where the robot reasons at a continuous level and also the abstract level about the task and about the presence of the human here. So since there is a task to perform and we are engineers, we want to perform it, we would like the robot to perform it in the best possible way. We want it to be efficient, we want it to be safe, but we want it also to be acceptable. We want the robot to produce, to synthesize behavior that is acceptable by the human, acceptable because it is predictable, because its intentionality is clear, it is legible, and also it is performing things that the human accepts or consider as helping. And for doing so, we are trying to incrementally endow the robot with decision and plan-based abilities, which will allow it to reason, to anticipate, to possibly produce proactive behavior or decide of proactive behavior. And this is performed not only considering the state of the task and of the environment, but also by predicting and reasoning about a human activity and also human mental state, what the human knows about me, what the human knows about my contribution to the task, and how can I involve and influence the human mental state so that we are able to conduct the task together. In a situation where the robot is sharing the decision, sharing the task, and also sharing the space. So they are in close vicinity, and this is also very important. We have adopted a constructive approach, and this constructive approach concerns two aspects of the system. From one side, what we call situation assessment and interpretation, the ability of the robot to correctly interpret through observation the correct task state, the correct context, including, as I mentioned already, the human partner mental state, what the human beliefs about the current state of affairs. And from a second aspect, the synthesis of robot behavior, the production of plans of motion that will allow the robot to perform its action, but also perhaps to plan about what or to anticipate what the human wants or is prepared or has decided to do by himself or herself. So I will go through, I would say, a number of illustrations to give some meat to this very general considerations that I've given so far. And this will concern a number of aspects, from the software architecture of such systems to investigations on models and algorithms that should be used inside the robot to allow it to elaborate its decisions. So in fact, what we have done is that we have developed and studied a number, I would say, of ingredients or independent or elementary abilities that we would like the robot to be endowed with. And this is presented here. For example, we need the robot to be able to monitor how the task is achieved by itself and by the human. We would like to equip the robot also with the capability to navigate safely and in a comfortable way between humans. This is what we call human-aware navigation. Another aspect is now manipulation of objects in the vicinity of human. We call it human-aware manipulation, okay, the ability to perform manipulation while taking explicitly the presence of the human and the contribution of the human to the task. Another key aspect is the notion of affordances. Also, as I mentioned already, these aspects of perspective taking, which is the basis for building an estimation of the human mental state. The robot tries through this process to place itself in the shoes of the human. And as soon as the robot is able to do this, it finds itself in a situation where it will have to manage divergent beliefs between itself and the human, and to use them first to assess them, and then to be able to act knowing them. And this is done using what we call human-aware planning, the ability of the robot to plan for itself and to anticipate the actions of the human, considering the human abilities, preferences, and needs. This is what we call human-aware task planning. All this are components, or I would say abilities, that are, I would say, integrated and articulated in a control architecture. Of course, nothing of this is completely finished. All these topics corresponds to very hot topics of research today. The applications here, we're showing some kind of applications that we have performed, some kind of context where we have applied and we have tested the ideas, the approaches, and the software that we have developed. Here, it's a robot guide in a Schiphol airport, which is able to guide in the wild, I would say, in open environment, passengers from one place to another to take them to the gate, for example. Also, we have worked on a human assistant robot at home that will perform essentially fetch and carry tasks for a dependent person. We have worked also of human performing a number of assistant tasks or activities, for example, here in a mall, in a commercial mall, for guiding persons or giving informations. And here, the last topic is a work that we have performed, is a research that we have conducted to study issues linked to human-robot collaboration in the framework of in industrial setting, the co-worker robot that shares the task with the human. I mentioned the control architecture. I will not go into details here because, for the benefit of time. This is what is under the hood, I would say, in our system. A number of components, I would say, achieving some of the abilities that we have seen before and articulated in a control architecture. What is important here is to see and to understand what is needed for this kind of robot. Essentially, the robot has, and this is AI, I would say, has the need to answer to a number of questions. What to do now? Who has to do? It could be the robot, it could be the human. Where to perform a task, when we have chosen what to do and who has to do, where it has been done. Also, and this is, I would say, trivial, when to perform a task. There are a number of moments where it is not convenient nor pertinent to perform a task. And the last point, which is very important, is how to perform it. Very often, there are different ways. There are many, many ways to perform a task, and some are far more preferable to the others when you take into account again, preferences and acceptability of the human. And this has to be, I would say, answered. These questions have to be answered at various levels of abstractions, okay, high level, or in the details of performing a task, and also with various time horizons, immediately, but also for mid-term or long-term, since we have to plan for future actions. And the problem here, we have the problem, we are in the quest of the good models and the pertinent, I would say, algorithm to allow the robot to answer these questions. And I will give some examples of this. So essentially, we have developed, I mentioned this already in the first slide, what we have called human-aware task and motion planning abilities, where we integrate in the robot the abilities to take into account the human preferences, needs, but also the efforts and even the comfort of the human. And for doing this, we have developed models which allow to refine what is this notion of mental state I was mentioning, and also the fact that very often actions can embed communication in order to allow the robot not only to perform an action, but also to convey the information associated to it for synchronization, for facilitations, or legibility. And also we have developed planning abilities for the robot at symbolic level, at the highest level of reasoning, but also at geometric level, how to perform the actions. And sometimes it is necessary to link both aspects to solve the problem because they can be, I would say, linked in an intricate way. Okay, the way to perform a task has consequence on what we are doing. When mentioning this notion of action and communication, indeed, these robots will have not only to achieve physical actions, they are there for that, for achieving physical actions, but also to communicate to the human so that the human can follow what is happening, can be comfortable and understand what is happening. So there are communicative actions per se. There are communicative actions that I mentioned integrated with actions, we call legible actions. And also sometimes there is a need for the robot simply, without doing anything, to exhibit its internal state, or for example, including its future plan, in order to inform, if needed or if asked, the human about what it is preparing to do. And this, of course, has to be done in a timely and pertinent way. So let's go through a number of examples that give some, I would say, illustration to this. The first one is this aspect of theory of mind. So this topic means essentially this. when I mentioned the fact that we need the robot to place itself in the shoes of the human, is in order to avoid the human to have a misinterpretation of such a situation. Okay, so we need a robot that is able to perform situation assessment, taking into account the human point of view, taking into reasoning on relative placement of itself and of the human, so that it can answer questions there. Can the human see me? Can the human see this object? Where should I place myself so that this situation can be seen by the human or not, for example. And for doing this, we are essentially not only allowing the robot, as we see here, to build a model of its environment, but also to reason about what the human sees from the scene. This is what you call placing the human in the shoes of the robot. So the robot is building its own, I would say, belief about the state, but also try to estimate the beliefs of the human while the task is performed. So we have developed an example which shows this ability that we have equipped our robot with. We have taken as an example the one very standard example in psychology, which is called the Salian Ant test, which is a test that allows to measure if a person, essentially a child, is able to attribute false belief to other persons present in the scene. So we have tried to implement this on the robot, and I will give you an example here of such a system. So let's imagine here we have a robot and two humans, blue and green, which are in the environment, and the robot is essentially an observer. So let's see what is happening here. Okay. So the robot is observing the scene simply and interpreting, trying to interpret correctly the situation. What we'll hear is on the right side of the screen, the model that the robot is building inside itself, so somehow. Okay, we show it here using 3D visualization. So the robot is now identifying the objects and recognizing the human and reasoning about objects present in the environment, and also the mental state of the human. Now green, the second guy, is coming. Now the robot will also try to estimate the mental state of the human about the current situation. Since green was near blue, the robot finds out that they have almost the same, I would say, view and the same beliefs about the state. Now what will happen is that while green is away, blue will update or modify the environment, and the robot is observing it. So as you see, there is a trick here. The blue has put an object in a place, the object that was here, in a place that is no more visible to him. Okay. So the robot is updating this and taking this into account. Now when green comes back, the robot is able, we'll see it here, is able to interpret correctly that human has noticed that the object which was here has disappeared, but is not able to know where it is because it is hidden to him. Okay, so the robot is able to attribute a correct belief to this human, and not the belief it has about the state. Okay, the belief he has from his point of view. And this is key in our system, because when the robot is equipped with this, it is able, if needed, to inform the human about the place where the object is in order to achieve its task and to allow the human to achieve its part of the task also. This is another example where the robot here not only builds this view of the scene, this is the human, these are the objects which are in front of it, but also estimate the belief of the human. This is the estimation of the robot of what the human sees. And as you see here, this human is able to see the object, the robot in the scene. This is, having this, the robot is able to compute, for example, here, to perform an action that is where, if it is asked to place an object, this object here, in a place that is reachable and visible by the guy who is sitting here, the robot is able to compute a position of the object and then to perform the pick and place operation in order to put it correctly. And this is because the robot is equipped with this ability to reason about the other and the ability of the other. And so we have equipped our robot with this ability to compute permanently, based on perception, the effort to see and effort to reach of objects in the scene from different agents, robots and human in the environment. Having this, the robot could now try to plan something, okay? Try to answer or to achieve a goal that is given to it. And what interests us here is situations where the robot has to produce a plan where not only it has to perform its task, but also the human is part of it. Okay? So the robot has not only to achieve its goal, but also to maximize plan utility so that to assist the human and to minimize the human effort. Okay, and for this we have a number of, I would say, techniques, algorithmic techniques and models, which allow to model, I would say, the needs and preferences of the humans, social constraints, and also try to promote fluency of the overall activity. For example, here, if the robot produces a plan for itself and also anticipate the actions of the human, and this is important, particularly if the human and the robot have to act together, which happens here because they have to exchange objects through a give-receive operations which involve the robot here, but also the human. We have two plans here that are coordinated and that are meshed, as we say, and where the human and the robot collaborate. Now, the social rules will take us to the situations where we'd like the robot to produce plans that avoid intricacies, avoid to make the human wait for the robot, and make a priori the robot in situation that it has to wait for the human. We have to minimize the effort and the disturbance to humans, which is the key aspect, since the robot here is developed to serve and help. Now, let's give another simple example, which is the handover. Handover seems a very simple problem, but it's not. Because, for example, if you ask the robot to hand over an object to a human in a situation where the human is not reachable, the robot has to compute and find a place where the transfer should be performed, minimizing the effort of the human and computing a place where the human can perform. And so here again, we develop robots that take into account not only their abilities to perform the actions, but also how humans can perform their task and try to minimize the effort of the human and make them perform them in the most comfortable way. You can have situations where the question of sharing the load within the human and the robot is open. Here, for example, if you have a strong guy who is in a hurry, we can do this. If you have an old person which accepts the robot to be intrusive, then the robot will do this. Okay, and so having this ability to balance between effort and needs of the human and also time constraints will allow the robot again to be pertinent and to adapt to the human needs. I think I'm going a little late. Yes, so I will have to accelerate a little here and summarize the last result I wanted to show here. So our idea here is robots that are able not only to produce a plan, but to produce what we call a good plan. A good plan means the ability for the robot to manage the joint task achievement, again, to ensure legibility and acceptability of its actions, and also perhaps to comply with conventions and to provide to the human coherent attitudes and behavior. All this can be seen as constraints on robot plans and on robot decisions. Let's take the example of sharing the space. It seems very simple here again, but here again, it's not that easy if we want the robot to perform in a way that is acceptable and legible. And for doing so, we have developed techniques where the robot is estimating and giving a kind of a score to a configuration. And so it is associating a kind of cost to the distance between itself and the human. If it goes closer to the human, this is acceptable only if the human accepts and wants the robot to come closer to him. Having this, we can develop real-time cost evaluation of such situations and have the robot avoid the human and not disturbing, or also adapting the human by essentially using cost-based motion planning techniques. And this has been applied. For example, this robot as this guide robot at Spencer Port that we have deployed is equipped with this planner. So it is avoiding to approach the humans. It is it tries to avoid to cut the trajectories of the humans. And more than that, it is also equipped with an ability with its head to explicitly show with its head where it is going next, and if it is observing the humans, so that to ensure the human about its abilities. This is performed here, where the robot looks at the human to simply to inform them that they have been seen, and also anticipate with its head where it is going next to ensure the human about what it is doing. Now, there are situations where the human has to contribute. For example, in a narrow corridor, it is not enough for the robot to do. It is not possible only for the robot to do the task. It has to take into account and even to influence the human so that they cooperate to solve the problem. Okay? And we have developed a reactive scheme where the robot here again not only chooses its task, but also anticipates what the human can do. So plans somehow for itself, for anticipating the human abilities. And our robot is, as you see here, able also to switch its behavior if the human has done the opposite choice. Let's see here the robot executing its path. Not only the robot avoids the human, but also it anticipates what the human will do to allow the human to be comfortable. Since I'm a little late, I think I will stop. I will switch to the conclusions. Well, I am in the conclusion to mention that these are my co-authors, and I'm mentioning also here my co-chairs in the NET chair. So we are studying these issues of pertinence, legibility, and ability to conduct, I would say, collaborative action with humans, including dialogue, with the need, of course, to have the robot being able to explain its past and future course of actions if asked so. Now, I have essentially spoken here about, I would say, model-based approaches to develop this kind of techniques. We are planning also to benefit and use learning techniques in the construction of the system. And this could be very beneficial, essentially in perception for object segmenters or picture detectors, but also for planners, essentially to develop operator models and new policies, and also heuristics for planners, and also possibly learning prototypical plans in order to, I would say, leverage the complexity of the planning computation costs. Now, concerning the criteria that I would like the robot to be able to take into account when planning and taking decisions, I have here, for your benefit, put here a list of of number of aspects we have looked at, which are linked to constraints, properties, and features that I can take into account. And I am here putting in green some of them that we have looked at them a little and introduced in our plans. Thank you very much for your attendance. Goodbye.